Hi, I'm Angela Jin, and I will be presenting Adversarial Scrutiny of Evidentiary Statistical Software on behalf of my collaborators, Rediet Abebe, Moritz Hardt, John Miller, Ludwig Schmidt, and Rebecca Wexler. In 2013, Mayor Herskevik, a Hasidic man living in Williamsburg, was convicted of a violent assault. The forensic lab involved in this case used a probabilistic genotyping software, or PGS, to analyze a DNA sample obtained from the victim's sneaker. The software's output concluded that DNA found in the sample likely belonged to Herskevik, and this incriminating evidence played a pivotal role in his conviction. However, countless factors pointed towards his innocence. No other physical evidence linked him to the crime, and alarmingly, the PGS tool used in this case was never tested on a population as genetically insulated as the Hasidic Jews of Williamsburg. In summary, Herskevik's conviction relied heavily on evidentiary statistical software his defense counsel could not scrutinize. And there are many additional concerns with the validity of PGS tools. For example, in multiple court cases, different PGS tools analyzing the same data led to divergent conclusions. Coding errors in one PGS tool affected dozens of cases in Queensland. These cases have led to many calls for independent assessment of the validity of these software tools, but publicly available information about existing validation studies continues to lack details needed to perform this assessment. Despite these concerns, PGS tools have been used in a total of over 220,000 court cases worldwide. And evidentiary statistical software are not just used for probabilistic genotyping. Tools have been developed and used for many other applications, such as breath testing, environmental audio detection, and toolmark analysis. Given that the US criminal legal system increasingly relies upon potentially invalid conclusions from evidentiary statistical software, we might ask, what mechanisms exist for validating these tools? There are some notable mechanisms. Two frequently discussed mechanisms are source code review and validation studies, but each of these faces significant limitations. Let's consider validation studies, a key factor considered in Daubert and Frye admissibility hearings in the US. First, this mechanism is currently limited by the lack of validation by independent groups, a group with financial or professional interests in ensuring that the tool is used can significantly impact how rigorous the validation is. Moreover, considering PGS as an example, the tool's validity depends on the scenario in which the tool is used, but validation studies, which are conducted outside the context of any specific case, may not test the tool's validity in scenarios similar to the defendant's case. And these limitations prevent defense counsel from fully scrutinizing evidentiary statistical software. This undermines the US criminal legal system, which relies on an adversarial system in which the prosecution is tasked with proving guilt and the defense is tasked with disproving the prosecution's case. In theory, the system as a whole seeks legal truth by pitting these two sides against each other in front of a judge or jury. But this system does not work as intended. Many scholars have already pointed out that this system is imbalanced in favor of the prosecution, and defense counsel's inability to fully scrutinize evidentiary statistical software worsens this imbalance. To tackle this issue, we ask, how might defense counsel adversarially test evidentiary statistical software? As I mentioned earlier, the US relies on an adversarial defense counsel to disprove the prosecution's case. We call this duty adversarial scrutiny. We see similar notions of adversarialism in the robust machine learning community. Adversarial robustness in ML is the study of how ML models fail under adversarial conditions such as changing subpopulations or adversarial input perturbations. Our contribution bridges these two notions of adversarialism by introducing robust adversarial testing, a framework for defense testing of evidentiary statistical software. At its core, robust adversarial testing answers the following question: Is the tool valid on cases similar to the defendant's? There are two key levers here. First, defining what it means for a tool to be valid. And second, defining what it means for cases to be similar to the defendant's case. These levers are represented by two key ingredients behind robust adversarial testing. The first key ingredient is the quality check function, which captures validity. The second is the family of distributions, which captures similarity. Let's now walk through each of these in more detail. Starting with the family of distributions, defense would choose characteristics of the defendant's case to specify the family of distributions. And defense would then evaluate the evidentiary statistical software on each distribution in this family. Let's see an example of what a family of distributions might look like. Recall Herskovic's story as I share some additional details from his case. The forensic lab estimated that 2 individuals contributed to the DNA sample that the police had recovered from the heel of the victim's shoe, which was found on a nearby roof 6 days after the crime occurred. The amount of DNA recovered was 97.9 picograms. Lastly, Herskovic is a member of the Hasidic Jewish population of Williamsburg, which is a uniquely genetically insulated community. Since the validity of the PGS tool depends on each of these characteristics of Herskovic's case, defense would want to use each of these distributions to test the PGS tool on cases similar to the defendant's. The second ingredient to prepare is the quality check function. Concretely, defense would choose an evaluation metric appropriate for the particular tool at hand. The check function would take as input the evidentiary statistical software and a distribution. The function would output whether the software passes or fails the quality check. For instance, defense might want to measure the PGS tool's inclusion error rate or false positive rate on a data set and check whether the error rate exceeds 10%. We combine these two ingredients, a distribution family and a quality check function, and propose the following formal definition. An evidentiary statistical software, A, passes F-check robust adversarial testing if for every distribution D in family F, we have check A, D equals pass. And we operationalize this formal definition in 3 steps. First, we would need to compile a large data set specific to the tool at hand. Next, defense would choose the family of distributions according to the defendant's case and instantiate the distributions using test data sets on which to evaluate the tool. Lastly, defense would choose a quality check function appropriate for the tool at hand and would use this function to evaluate the tool. We think robust adversarial testing is useful for several reasons. First, it connects 2 active communities and creates synergies between them. For instance, it provides new, well-motivated problems for the robust ML community to work on, and in turn, defense counsel can apply findings throughout the life cycle of a case. Our proposal also provides a framework for audits of statistical software while extending the scope of work in algorithm accountability to include evidentiary statistical software. We think this proposal is feasible because defense counsel is entitled to present arguments relevant to the case, and the robust ML community already has frameworks for testing statistical models on families of subpopulations. However, drawing from discussions with public defenders who informed much of our work, current structural and institutional barriers would prevent us from implementing robust adversarial testing in practice, so we discussed additional proposals to overcome those challenges. First, trade secret arguments in courts significantly limit defense access to relevant data they would need to perform robust adversarial testing. So we echo previous calls for eliminating trade secret barriers that currently limit defense access. Even with full access to data, under-resourced and overburdened public defense offices would face additional difficulties in performing robust adversarial testing, so we propose that the US government provides funding for these offices to hire specialized technical staff to perform in-house testing. Since our framework would require significant time and technical expertise that many defense attorneys may not have, we additionally propose that the computer science community build off-the-shelf testing tools that defense counsel can easily use. And the ML research community can help by performing audits of evidentiary statistical software to highlight issues with validity, building off-the-shelf testing tools, volunteering technical support through organizations like PD Query, who connect STEM experts with public defenders, and writing affidavits and cross-examination questions that can help illuminate issues with the validity of evidentiary statistical software. And this concludes our presentation. For more details, please see our paper. On behalf of our team, thank you.